Okay, students, welcome again to the physics period. And today we are going to look onto the topic of mechanics, and the subtopic we are going to look is the rotational dynamics, particularly to the applications of theorems. I'm Cyprian Mgina, a physics teacher. First of all, I really believe you have enjoyed the first part of this lesson, where I believe you have looked those two theorems with regard to the moment of inertia of a body. So those are the two important theorems that you are supposed to have understood them. What we call the parallel axis theorem, the parallel axis theorem, and the perpendicular axis theorem. Perpendicular axis theorem. These are the two theorems which are very important for you students to understand. And really, to this particular lesson, we are going to take you a bit more level where you can be able to solve some more difficult problems by using the two theorems here, but sometimes it might also need you to combine them to solve for those kind of the problems. We're just going to look a very simple case. For example, if you are given, let's say, a circular disk, you are rotating a disk about in an axis which is passing perpendicular through its plane, passing through its center. So we can just have, for example, a circular disk like that. Could have a circular disk like that. So that we are having an axis that is just passing through its center of gravity, G. So we are looking the moment of inertia through that particular axis. If this is a disk, then I believe the moment of inertia, I, is just equal to a half times mass times the radius squared. If I'm taking this particular body, this disk to be having a mass m and its radius to be equal to a. But sometimes, if you are looking, let's say you are rotating the same disk about in an axis which is passing, let's say, at its rim, perpendicular with the first axis, which is just passing at the center. Both of the two axes are perpendicular to the plane of the disk. Then here you are just going to use what we call the parallel axis theorem. So that if you need to determine the moment of inertia, which is just passing there, the moment of inertia which is just passing there, then you really need to use the parallel axis theorem. The parallel axis theorem says that if you are rotating a body, if you are having an axis passing through a body, it's passing through a body at its center of gravity, and its moment of inertia is just equal to Ig. Then, whenever you are having another axis parallel to this one, passing at any point through that particular body, let's say you are having, for example, you are having just like a mass, like a stone or whatever. We are having an axis which is just passing through its center of gravity, there to be equal to, the moment of inertia there is just be equal to Ig. Now, whenever you are having another axis parallel with this particular first body, let's say just passing at that particular point, with the distance, the separation distance between the two axes is just equal to h. Then the new moment of inertia through the new axis, parallel to the first one which is passing through the center of gravity, I, will just be equal to the moment of inertia through the first axis that is passing through the center of gravity plus m times h squared, where h is the separation distance between the two axes and m is the mass of that particular body. And I believe you know that by definition of the moment of inertia just equal to a product of the mass times the radius squared, r squared, r being the distance from where the axis is just passing to the center of mass of that particular body. And sometimes we are just using what we call the radius of gyration, and that's why the generalization of this really gives us m times r squared, where r is what we call the radius of gyration. Okay, that is for the parallel. That is for the parallel axis theorem. Now let's come back to our disk here, and later I'll be able to introduce to you for the perpendicular axis theorem. But I believe in the first lesson you have really done this. So now, if I'm looking the moment of inertia through an axis which is just passing on its rim, but perpendicular to the plane of a disk, parallel with the first axis that is just passing through its center of gravity of the same disk. So the moment of inertia of this particular axis, I, will just be equal to, we are using now the parallel axis theorem. So I'll be taking the moment of inertia through an axis that is passing through the center of gravity plus m times h squared. And for this case, the h, the distance separating the two axes, is just equal to the radius of the disk, which is equal to a. So for this case, h here will just be equal to the radius of a disk, so that we could be able to find that if I know the moment of inertia of the body through the center of gravity perpendicular to its plane is just equal to a half times mass times radius squared, then here will just be equal to mass, h is equal to a, will be equal to that much. So that if we add up here, here I'll be having 3/2 times mass times radius squared. So this will be the moment of inertia. Let me call this to be the moment of inertia, x, which is just passing at the point on its rim perpendicular to the plane of the same disk. So its moment of inertia will be equal to this much. Now, for example, I'm looking now the moment of inertia, let's say, of an axis which is just passing to the point on its rim, but now not perpendicular to the plane of the same disk, but it is just passing along, let's say, parallel with an axis that is just passing along the plane of that particular disk, but on its rim. So here I will be having an axis which could just be passing, let's say, at that particular point. So I might be talking about this particular axis. That is an axis which is really that if I could be having another axis passing over a plane, this will be the axis which are just passing over the same plane. So to determine the moment of inertia of this one here, let me call this to be IO. To determine the moment of inertia IO for an axis which is just passing parallel with the plane, but on its edge, that is on its rim, we need now just to look for any particular moment of inertia which could just be passing, let's say, through the center of the same disk. Let me call this to be I1, for example. The moment of inertia for an axis which is just passing through the center of that particular disk along its plane could just be the same as any particular axis which is just passing over the same plane through the same point, or that is through the center. So here simply I can take two axes which are perpendicular to each other. Let me take this I1 and let me take another axis passing through the same point, so that I'm having another axis here. Let me call this to be an axis I2. So I'm having the two axes. If I could be able to draw in a very good diagram again here, then we could have something like that. That I have already obtained a moment of inertia through an axis that is just passing through the center. Then here I'm calling this to be IG, and I have already obtained the moment of inertia through this axis. I've called this to be IX here. Now I'm looking the moment of inertia through an axis that is just passing over its edge here. I've called this to be equal to IO. Now to establish to find this moment of inertia, I'm going to draw the moment of, I'm just going to draw an axis passing over its plane. But any particular axis passing over that particular plane will be, whenever a disk is rotated about that part, any of the axes passing over its plane through its center, they will just be of the same because they are all passing through the center. So I can just pick any two axes which are perpendicular to each other. Let me take the first one, as I've just drawn here, as I2 and the I1. So let me take this axis here as I2, and the first one perpendicular to this one, let me take the one which is just passing through the center, this one to be equal to I1. So as long as I1 and I2 are perpendicular to each other and they are passing over the same disk over the same plane through the center, then the two moments of inertia will just be the same. That is, I1 will just be equal to I2. Let me call this to be equal to I, for example. So now I just want to establish I just want to use now the perpendicular axis theorem to determine the moment of inertia IO. By a definition, as you have already learned in the first lesson, for a perpendicular axis theorem, it says that whenever you are having some two axes which are perpendicular to each other, the moment of inertia of if you know the moment of inertia of the first axis and you know the moment of inertia of the second axis, that if I'm taking this to be a body and you know the moment of inertia of a body through the first axis, let me call this to be equal to IA, passing through a certain point, and you have another axis, perpendicular to the first one passing through the same point, call this to be equal to IB. If the two axes are perpendicular to each other, then the moment of inertia of an axis which will cross through the same point but perpendicular to the rest of the other two, for example, here now I'm talking about this particular axis, if I'm calling this to be an IC, then the moment of inertia whenever a body is rotated through an axis IC, therefore this will just be equal to the moment of inertia of the first axis plus the moment of inertia of the second axis, as long as the first and the second and even the third axis, they are all perpendicular to each other. And this is what we call the perpendicular axis theorem. And it's the one which I'm just going to apply it there. So here, I'm looking the moment of inertia through an axis that is just passing on its edge. But first of all, I need to establish the moment of inertia of an axis that is just passing over the plane of that particular disk. Now, to determine that, then I'm saying that the moment of inertia of any particular axis passing over a plane will just be the same, so that I1 is equal to I2 is equal to I. Now, as long as, if I'm using a perpendicular axis theorem, then it means that the moment of inertia through an axis passing perpendicular to a plane through its center, therefore this will just be equal to the moment of inertia of that particular axis plus the moment of inertia of the second axis. But I1 and I2 are the same. Then this will just be equal to I1 plus I2, which are the same. This will just be equal to 2I. But the moment of inertia through the center of gravity, this is just equal to a half times mass times radius squared. So it means that by a perpendicular axis theorem, it means that the moment of inertia through the center of gravity, this will just be equal to twice times the moment of inertia of any particular axis that is just passing over a plane. My interest is to determine what is I. So I here will just be equal to the moment of inertia through the center of gravity divided by 2. But the moment of inertia through the center of gravity, this is just equal to a half times mass times radius squared. So I divide by 2. So I'm getting an axis passing over a plane of a disk through its center. This will just be equal to a quarter of a mass times radius squared. So if I have obtained that, it means that that particular axis at any particular direction can be parallel with an axis that is just passing on its edge. And then I'm going to use the parallel axis theorem. To use the parallel axis theorem, the distance separating the two axes. The distance separating the two axes will just be equal to the radius of a disk. So using the parallel axis theorem, then I'm just going to use this particular expression. But the axis that is just passing through the center of gravity over its plane now just be equal to this much, which is just be equal to a quarter times mass, radius squared, and L just be equal to m. And this h is the distance separating the two parallel axes, which is equal to the radius, is just be equal to that much. And if you add up here, you are going to get 5/4 times mass times radius squared. So this will be the moment of inertia of a body rotated through an axis IO. So this will just be equal to IO. Okay. This is a simple example. We can go to another stage whereby we could just be able to determine the moment of inertia of a rectangular block with this particular side. So we could be having a rectangular block like this with various sides. We could have this particular side, let's say this to be equal to 2a, and this side it could be equal to 2b, and this side could just be equal to 2c. And here we need just to look for the moment of inertia passing through its center. Then we could have an axis passing through its center, and we could have another axis that is just coming away from the center there, and we could have another axis which is just coming from the center of that particular side to this particular direction. Then let's call this to be x, and this to be y, and this to be z axis. So that we need now just to determine the moment of inertia of any particular axis. So if we are going to rotate about the z-axis, then I could be able to obtain this moment to be the moment of inertia about z-axis. If you rotate about an x-axis, then we could be able to get the moment of inertia ix about whenever a rectangular block is rotated about x-axis. So the same, whenever it's rotated through y-axis, we are going to obtain the moment of inertia IY whenever a rectangular block is rotated about y-axis. Now what we're going to do is something like this. We might be asked to determine, let's say, the moment of inertia whenever it's rotated about the z-axis. Now, my dear students, you need now just to understand the way how you can be able to obtain the moment of inertia of the normal rectangular board or lamina, just like this. If this is just like a cardboard with a side, let's say 2a, and here it is 2b, and you are let's say we are rotating, we need to determine the moment of inertia whenever it's rotated about an axis which is just passing through that particular position, let's say through its center, passing through its center. So you need now just to know on how you can be able to obtain the moment of inertia whenever you are rotating this particular body through that particular axis, passing through, let's say, through the center of gravity with that particular axis, which is moving over the plane and be rotated in that way. So through that particular example will take you to a level of where you can be able to obtain the moment of inertia of such a rectangular block whenever it's rotated about any of the axes, whether through x-axis or y-axis or z-axis. Now let me take you quickly with what I believe you have understood, or you could be in a position to find the moment of inertia whenever this particular block or cardboard is rotated about in an axis passing over its plane through its center, with an axis that is just passing over its plane. What we're going to do is that if this particular block is having a mass m, and the size of it are 2a to 2b, then what we are going to do is that we are just going to establish a very small element here of a thickness dx located at a distance x from that particular axis. And you need to establish now the mass of this particular part. So you all know that the whole of this particular size, that is 2b times 2a, that area really corresponds with the mass m, which is equal to 4ab, corresponds with the mass m. But here I'm having the length 2a and the thickness dx. So 2a times dx, that area, you need to find as to what mass will it correspond to. So that particular area, which is equal to 2a times dx over 4ab, 2a dx over 4ab times m, this will be the mass of this particular small element. So the mass, let's say, the mass of that particular element will now just be equal to 2a dx over 4ab times m. And if you write in a very good way, you are going to get the a and a will cancel, and will be having m dx over 2b. So this will be the mass of that particular element. And we are having several of these elements from that end to where the axis is just passing. So you really need now just first of all to determine the moment of inertia of this element about this axis. By a definition, the moment of inertia I is equal to mass times the distance squared, or the distance from the axis of rotation squared. And if now I'm looking, let's say, for this particular element, the mass for an element is this much, which is equal to capital M, the mass of the whole rectangular plate, will be equal to m dx over 2b. This is the mass, and the distance now, that is x. The distance from that particular axis, that is x. So we multiply times x. Now the distance squared will be equal to x squared. So this is the moment of inertia for such a single element. But we are having several of them. So to determine the moment of inertia from this axis to that end, then you need to do an integration. So you'll have just to integrate this from this part to that part, a distance which is equal to b, so from 0 to b. But having obtained the moment of inertia of this part, then there is another an equal length of the other side. So you need to multiply by 2. So the moment of inertia I here will now just be equal to 2, and the integral from 0 to b of that particular expression. But remember, let me write first of all, I'm having m dx times x squared over 2b. But m and 2b, these are constant, can be taken outside. We can take them outside, so that we are going to have the 2 and 2 will cancel, so we can remain with m over b, an integral from 0 to b, and there will be having x squared dx. And actually here will be having m over b, here will be having x power 3 over 3. So we substitute from 0 to b, and actually we'll be having m over b, and inside there will be having b power 3 over 3 minus 0, so we'll be remaining with that. And actually I'll be having mb squared over 3. So the moment of inertia I, the moment of inertia I, for a body to be rotated about an axis passing through its center along a plane to the side of 2A is be given by that much. So it means what? So it means that whenever I'll be taking another axis of rotation passing through the same center of gravity, rotated it through this way, that particular moment of inertia will just be having the same expression as this. So if I'm taking this to be I1, then the moment of inertia I2 through an axis perpendicular to the first one over the same plane passing at the center of that particular body, then instead of a B here, I'll be having an A. So it will just be equal to M into A squared over 3. So this will be the moment of inertia of the second axis passing through the center of the same body at the center of gravity, but over the plane of that particular body. So such that finally, whenever I'm looking the moment of inertia that is just passing now perpendicular to its plane, using the perpendicular axis theorem, it will now just be the sum of the two axes. It will just be equal to the sum of the two axes. That is, that particular moment of inertia I will be equal to the moment of inertia of axis 1 plus the moment of inertia of axis 2 using the perpendicular axis theorem, of which, if I'm just going to add this and this very quickly, I'll be getting m over 3 into A squared plus B squared. This will be the moment of inertia of that particular axis that is just passing perpendicular to that plane. And that is the knowledge you are just going to use now to determine the moment of inertia of an axis, of which I've already mentioned it to you earlier. So having known this, or if I've just made you to remember how to obtain this, then whenever we are embarking to determine the moment of inertia, let's say through this axis which is just passing, let's say through this axis to a z direction, if we're looking or determining the moment of inertia of such a rectangular block through this axis which is just passing through an axis to the to a z direction, then what we need to know is to know the moment of inertia that is just passing through an axis, x-axis, and the moment of inertia that is passing through the y-axis, and later be able to use the perpendicular axis theorem to determine the moment of inertia that is just passing through the z-axis. And we can be able to do this as quickly as possible as it follows here, such that if I need to determine, let's say, the moment of inertia, if I need to determine the moment of inertia about the moment of inertia, let's say, through x-axis, then we could just be like taking the slices of rectangular plate with the side 2B, 2C all over moving this way. And whenever you rotate about that particular axis, now we'll just be able to produce an expression very similar to that one, such that the moment of inertia about x-axis will now just be equal to m over 3 into m over 3, m being the mass of that particular block. If I'm taking the mass of the block is equal to m, so m over 3, now here will be equal to b squared plus c squared. This will be the moment of inertia for this block whenever it's rotated about x-axis. Remember, this x-axis is just passing at the center of this particular rectangular plate surface. So the same way, if I'm going to look the moment of inertia whenever it's rotated through the y-axis, remember the axis is just protruding at the center of this particular surface. With the side here it is 2B and this side is 2A. So that this moment of inertia will be equal to m over 3 into a squared plus b squared. But if now I'm talking about a cube, if now I'm talking about a cube, it means that this size will be the same as that size will be the same as that size. So it means that 2A could just be equal to 2B could just be equal to 2C. And then if that is the case, then it means that it's the same as saying that A is equal to B is equal to C. And if that's the case, I can take it to be A throughout, for example. Then if I'm talking about a cube rotated about that particular axis, so it means what? It means that this moment of inertia through an x-axis, if I'm taking B is equal to C is equal to A, then this could just be equal to m over 3, and here it is a squared plus a squared. This will just be equal to 2a squared, or simply to be equal to 2 over 3 with mass a squared. So the same thing could be applicable for the moment of inertia rotated for the body whenever it's rotated about the y-axis, which will just be the same as 2 over 3 with ma squared. Okay, students, as we have already seen, the moment of inertia through x-axis is equal to this much, and if it's a cube, is equal to that much. The moment of inertia whenever it's rotated through the y-axis is equal to this much. If it's a cube, takes us to this particular expression. So it means that also the moment of inertia through the z-axis, the moment of inertia through the z-axis will also be equal to m over 3. Through the z-axis will be equal to m over 3 into a squared plus c squared. If a is equal to c, then this will just be equal to 2 over 3 with ma squared, if I'm talking about to be a cube. Okay, so whenever we are looking the moment of inertia through this particular axis, as long as know the moment of inertia through the z-axis, which is equal to this much, if I'm talking about a cube, then I can be able to do the moment of inertia about this axis, which is just passing at the one corner of that particular rectangular block or a cube. So if I'm still considering this to be a cube, then I need to know the distance that separates the two axes, which is equal to h. And from the Pythagoras theorem, as what I've already derived previously, the h squared will be equal to 2a squared. And from the perpendicular axis, from the parallel axis theorem, then we just found that this moment of inertia will be equal to the moment of inertia through an axis that is passing through G plus m times h squared. Now the moment of inertia which is just passing through G, or that is a moment of inertia through a z-axis, this is just equal to, if it is a cube, this is just equal to 2 over 3 mass times the distance a squared. And h, remember, h is equal to 2a squared. So we multiply here times m times 2a squared. And if that is the case, it takes me to 2 over 3 ma squared plus 2 ma squared. 2 ma squared. And therefore, here we can be having to be 3 over 2 ma squared. And here will be equal to 6 ma squared, which takes me to an 8 ma squared over 3. So this will be the moment of inertia about this particular axis, which is just passing at the edge, such that whenever you're rotating a cube, then the moment of inertia, whenever it's rotated about this particular axis, its moment of inertia will be equal to this much. And the same problem can be solved if at all this is not a cube. It is still a rectangular block with side 2a, 2c with the 2b. You can as well be able to follow the same procedure and be able to obtain what will be now the moment of inertia whenever a block, the same rectangular block, is rotated about this particular axis. Okay, students, now having looked at all of those examples, we can now just be able to go and look now another challenging question that takes us to a new level of solving some more difficult moment of inertia, rotation of some bodies with various axes located at different positions. Now here we are having the solid cylinder. Okay, students, let's go to the question number 1. A goes like this. Derive an expression of the moment of inertia of a solid cylinder of mass m, radius a, and length l about an axis that passes through its diameter at one end. B. Use an expression obtained in part A to compute the moment of inertia of a solid cylinder given that its mass, radius, and length are 1.5 kilogram, 5 centimeter, and 10 centimeter respectively. This is question 1. We are having a solid cylinder like that. So the central axis of the cylinder is the one which is just passing at the center like that. Now we are given that this cylinder is of a length L and is of a mass M and its radius is equal to A. The radius for this is equal to A. So our axis is just passing through its diameter at one end. So we can take this to be the side where the axis is just passing. So we could be taking the axis is just passing at the diameter. It means that it's just passing through its center. So we're having this to be the axis. And so we need now to determine that particular moment of inertia through that particular axis. Now, as you can be able to see, this is the solid cylinder. This is the solid cylinder. And to determine the moment of inertia through this axis which is just passing through its diameter, then we need now just to use use what we call the parallel axis theorem. So we just take any particular slice. If we are dividing this particular cylinder at various slices, and I can pick one slice at this particular location. Let me take this to be the slice at that particular location. Let's say to be located at a certain distance X from that end, and what I need now is to establish the mass of this particular disk. What I need here is just to establish the mass of this particular disk. And to establish the mass of this particular disk, then first of all we need now just to understand the actual volume of this particular disk. For example, if you are given the mass per unit volume to be equal to a small m, if m is the mass per unit volume, then the mass of a cylinder, we are taking the surface area times this particular thickness. Let me take this thickness is dx. So the surface area, the mass of that particular element will be equal to the volume, that is pi, and the radius squared times dx. This is the volume. So we take with a mass with its mass to be equal to this much, and this will be equal to the mass of that particular element. Okay, so that this is the mass of an element. But remember, we had just done it previously. Whenever we're looking the moment of inertia of a disk about in an axis passing through its center along its plane, we are just obtained to be equal to a quarter times mass times the radius of that particular disk squared. Whenever we are talking about a disk with an axis that is just passing over its plane through its center, the moment of inertia we are obtained to be equal to that much. Now, it's just the same as this one. Whenever I'm having an axis passing through the center and I'm rotating this particular cylinder in this way, so that this particular moment of inertia of this particular disk, whenever it's rotated about this axis, will have just to follow the same formula. So that the moment of inertia now, the moment of inertia of this particular disk, whenever it's rotated about, whenever it's rotated about this particular axis, then we will just be able to be equal to that much. where the mass here is the mass of an element which is equal to this much. So that if I'm talking about the moment of inertia through an axis of this particular body, the moment of inertia of this particular element rotated about, this axis, let me take IE, then this will just be equal to a quarter of mass. The mass is of this much, which is just be equal to pi a squared dx times m, the mass per unit volume, times a squared. So here we multiply times a squared, and therefore, if I'm looking now the moment of inertia through this particular axis, then I'm just going to use the parallel axis theorem. So let me take this particular moment of inertia which I'm looking for. So the moment of inertia, I, by the use of parallel axis theorem, the distance that separates the two axes is just be equal to x for that particular case. Then we're going to have something like this, that I'll be having, if I'm taking a here, I'll be having 1 over 4 pi a power 4 m dx. This will be the moment of inertia through this axis, i.e., plus the moment of inertia, plus m times h squared. M being the mass, of that particular element, then we are just going to have, for an expression of mh squared, this will just be equal to pi a squared times dx, the volume, times the mass per unit volume, and then we are taking the whole of this much, we are multiplying times x. X being the h, so it will be equal to x squared. And that's an expression. So we are going to have here to be equal to 1 over 4 pi a power 4 m dx plus mh squared, which will just be equal to pi a squared mx squared dx. This is the moment of inertia. Okay, now, having obtained the moment of inertia I, then we could just be able to find that here we are now just going to do some integration so that we could be able to obtain the moment of inertia of all elements from 0 to L. L being the total length of our solid cylinder. So really here we need just to integrate from 0 to L of this expression, which is equal to 1 over 4 pi a power 4 m dx, and also here we have to integrate from 0 to L of that much, which is equal to pi a squared mx squared dx. And the 4 pi a and m, these are constant. 1 over 4, so we can take outside 1 over 4 m times pi a power 4 1 over 4 m pi a power 4. So we're just going to have dx from 0 to L plus, you can be able to see here also the pi a squared m, the pi a squared m, this can be taken outside from 0 to L, and inside there we're just going to have x squared dx. So integrating here, we're just going to have 1 over 4 m pi a power 4, and here we'll be having, we're just going to have x, substituting from 0 to L, we're just going to have L, and here we're just going to have x power 3 over 3, so it'll be equal to pi over 3, will be equal to pi over 3 a squared m L power 3. Pi over 3 a squared m L power 3. And this will be giving us the moment of inertia of that particular body. And if we are just going to simplify and write in a very good way, we are getting this expression here. Okay, as long as we know this m is the mass per unit volume, therefore our total mass m of a body will be equal to pi a squared. Pi a squared will be equal to pi a squared, the surface area, pi a squared times m times L. Pi squared a squared times m times L. So this will just be equal to the total mass. This will just be equal to the total mass, which we can call this to be equal to capital M. And therefore you can be able to find that the moment of inertia I now can just be reduced now. From this expression, you can be able to find that if you take pi a squared L with m as a capital M, here you'll be having m a squared over 4, m a squared over 4. Remember, another a squared had been absorbed there, and plus the whole of this will be equal to ml squared over 3. Okay, and therefore we can be able to simplify this. M can be taken outside, and inside we can have a squared over 4 plus L squared over 3. As the moment of inertia of a cylinder about in an axis which is just passing through its diameter at one end. So it's given by this particular expression. And we can now just be able to go and look for the second part. Use an expression obtained in part A to compute the moment of inertia of a solid cylinder, given that its mass, radius, and length are 1.5 kilogram, 5 centimeter, and 10 centimeter respectively. So here, our expression obtained is equal to this much. And the mass m given is 1.5 kilogram. So that the moment of inertia I will just be equal to m, to the mass, which is 1.5 kg. And inside there, the A, remember A is the radius. The radius is 5 centimeter. That is 5 times 10 power negative 2. So the whole of this, we are squaring that, divided by 4. Plus L, the length of that particular cylinder is given to be equal to 10 centimeter. So we are taking 10 times 10 power negative 2 over 3. And the whole of this, we square this, okay? So we can be able to compute for that. And then from there, it's a matter of just using your calculator. So if we are just going to use your calculator, you are just going to get something like this. That this will just be equal to 1.5. And inside there, we are taking 5 times 10 power negative 2. We are going to get 5.9. 5.9325, 10 power negative 3. 10 power negative 3. This is kilogram meter squared. This is the moment of inertia of that particular solid cylinder whenever it's rotated about that particular axis. Okay, students, let's go for the homework. This is the question for your homework. There are two parts, A and B. A goes like this. Show that the moment of inertia of a rectangular plate of mass m with sides 2a and 2b about an axis through its diagonal is 2ma squared b squared divided by 3a squared, 3 into a squared plus b squared. This is A. Okay, part B of the same question for your homework. The mass of the above rectangular plate now is 8 kilogram, with its length be 24 centimeter and the width of 12 centimeter. Now compute its moment of inertia about the same axis of rotation. So here we are given the rectangular plate. I'll be able to give you a hint, and I hope you can be able to do it at home. That we are given, here is the rectangular plate of mass M. So if it's a rectangular plate, then it is a plate which is just like that. It's a rectangular plate of mass M. And the sides, these are 2b by 2a. So now we are being asked to show the moment of inertia of a rectangular plate of a mass M. We are taking this to be having a mass M. The mass of a plate with that particular sides and about its diagonal. So the moment of inertia, the axis of rotation is just passing through its diagonal. That is from one corner to another corner, or from this corner to this corner. So we are having the axis of rotation to be passing about a diagonal. So we are looking now, the moment of inertia, whenever this particular rectangular plate is rotated about this axis, which is just passing through the diagonal. Now you need just to show that this moment of inertia, from what we have already looked previously, is just equal to 2 into m a squared b squared over 3 into a squared plus b squared. So you need to show that that particular rectangle, that particular moment of inertia about this axis, which is just passing through the diagonal, is equal to this much. And finally, you will just be able to compute if the mass of this particular body is 8 kg and the length, which is 2a, the 2a is equal to 24 centimeter, and the width, which is 2b, that is equal to 12 centimeter, then you can be able to substitute what will be a, what will be b, and then be able to obtain what will just be the moment of inertia about that particular axis, which is just passing through that particular diagonal. I hope, my dear students, you can be able to do that question comfortably if you really have understood the previous stages when I was just introducing it to you, all what we have just learned today. Thank you, students. There are so many challenging problems, but I believe this is just the beginning. You can be able to know that through perpendicular and parallel axis theorem, it can really be able to take you to a more advanced level of where you can be able to solve so much complicated problems with regard to the moment of inertia of a body. So thank you, students, for today, and see you next time.